6 for everyone classes. This is your Satish. So in this section we can see build your concept 3 from the topic gravitational field intensity, and the chapter is gravitation. Here we are going to find a null point, which means at a particular point the net field intensity due to the given masses should be equal to 0. And here we are going to find the position of the null point. Let us see the situation. Here we are taking two bodies. The one is the earth, which has the mass capital M, and we know the mass of the earth, which is how much? 6 into 10 power 24 kilogram. You can take the mass of the earth is equal to 6 into 10 power 24 kg, and the second object is the moon. And here we are taking the natural example. We are finding the null point between the earth and the moon. In between, somewhere else we will get the null point. And the second mass is the moon. We can take it as small m, whose mass is equal to nearly 7.35 into 10 to the power of 22 kg. And if you compare these two, you will get the mass of the earth is equal to 81 times the mass of the moon. In the examination, they might be given these masses, but we need to remember the relation between the mass of the earth and the moon. How much it is? The mass of the earth is equal to 81 times bigger the mass of the moon. Please remember this one. And the distance between the mass of the earth and the moon, which is denoted by d, and whose value which is equal to 3,85,400 kilometers. How much it is? 3,85,400 kilometers is the distance between the earth and the moon. We can take it as the separation between these two from their centers. How much? 3,85,400 kilometers. Now, we are interested here to find the gravitational field intensity in between these two. Somewhere else you will get the null point where the field intensity is 0. We don't know that point. Let it be taken at point P. Now, at the point P, due to the earth mass, the field intensity is acting towards the mass. Let it be taken E1. So E1 is the gravitational field intensity at the point P due to the earth mass. Similarly, at the same point, the gravitational field intensity due to moon will be acting towards the moon, and it is being taken as E2. And if these two values are equal in magnitude as they are opposite, these two will get cancelled. There you will get the resultant field intensity is equal to 0, which is called as a null point. For to get that position, let it be taken this point, the distance from the center of the moon, we can take it as x, and the remaining distance, which means from the center of the earth to that point, comes as how much? D minus x, where d is the separation between the two given bodies, and x is the position of point P from the center of the moon, and d minus x comes as the distance to the same point from the mass of the earth, from the center of mass of the earth. Now we can write the field intensity equation E1 and E2. How much E1? We can write E1 is equal to, E1 is the field intensity due to the earth. We can write G into M divided by how much the distance from the center of the earth? D minus x. So it comes as D minus x whole square. And whose direction is towards left? That is denote the vector which is acting towards the center of the earth, that is towards the left direction. Similarly, write down the field intensity due to the moon E2 is equal to G into the mass of the moon divided by the distance is how much? From point to the center of the moon is x. Let it be taken x square. And whose direction is towards the moon? That is towards right direction. And net field intensity you will get in the vector form. We can write the resultant field intensity ER bar is equal to E1 bar plus E2 bar. The field intensity, the resultant field intensity at any point is the summation of all the field intensities due to all the masses. And if you take the magnitude of it, I can write the magnitude, the resultant magnitude, which is equal to E1. E1 is towards left, you can take it as negative sign. So minus how much? E1. And E2 is towards right, to take it as a positive direction, plus E2. And we are expecting at the point P, the resultant field intensity is 0, which is equal to 0. So which means that what you are getting finally, E1 is equal to E2. Their magnitudes are equal. Now we need to equate these two equations to get the position value, x value. So let us equate. Here I am equating both the expressions. So Gm divided by d minus x whole square is equal to g into small n divided by x square. And what you will get here with this, if you simplify this one, g get cancelled out, and d minus x by x whole square, this term goes to this side, and small m will come this side, which is equal to capital M divided by small m. And taking square root on both the sides, d minus x by x, which is equal to under root capital M divided by small m. Further, if you simplify, finally you will get x is equal to d upon under root capital M divided by small m plus 1. You see here, capital M is the mass of the earth, or the first object. Small m is the mass of the moon, second object. And where x is the distance to the point P, from where? From the second mass, nothing but the mass of the moon. There you can relate these two. So from where we are taking this x, this is important. We are defined the x to the point P from the second mass. There you can see x is always distance to the given point P from the mass which is placed at the denominator from the smaller mass. Who is the smaller mass here? The mass of the moon. You need to take care of these two parameters, x with the small m, or the denominator mass. And if you substitute all the values here, you will get the null point. So let it be taken. So which is equal to d divided by under root. How much is capital M in terms of small m? 81 times of small m. Let it be taken 81 small m divided by m plus 1. Small m get cancelled. Under root 81. You will get 9. 9 plus 1, 10. Which is equal to d divided by 10. So you got the null point, which is very closer to the second mass or the smaller mass. How much distance? D by 10. If it is asked how much is the null point distance from the heavier mass, you need to take d minus d by 10. How much will you get? 9d by 10. You see, the null point is always been closer to the smaller mass. It is been just like the center of mass concept, where the center of mass is lying towards the heavier mass. But here we are equating where the two field intensities due to the two masses are being equal and opposite. There you will get a null point. This point is always closer to the smaller mass. So in this way we can find for any two given objects, whether it is a point masses or the extended objects where it is the form of spherical in shape, there we can use this formula. How much? x is equal to d upon under root m2 by m1 plus 1. The plus symbol indicates that the nature of the force is always attractive. Always you will get the null point in between the two masses. There is no chance to get the null point out of the two bodies. If you take any point outside the field intensity direction, both the field intensity directions will come in the same direction. The same direction, never you will get the field intensity, resultant field intensity is 0. So let us see the one more topic from the same concept. Let us see the situation. Here I am taking 6-point masses which are placed at the vertices of a regular hexagon. There you can see 1, 2, 3, 4, 5, 6. 6 equal masses which are placed at the vertices of a regular hexagon, and whose side length you can take it as small a. And we are going to find the resultant field intensity at the center of the regular hexagon, how much it is. And directly we can say here the field intensity comes as 0 for this situation. For the regular bodies of the equal masses, whether you can take a triangle of equal masses, at the centroid the field intensity comes as 0, you will find the null point there. And here also, for the equal distribution of masses at each and every corner of the regular hexagon, the field intensity again at the center comes as 0. Here you will find the null point. Let us see once. And here is the point at the center. The field intensity due to this mass will be acting in this direction. Let it be taken it as suppose E1. Similarly, the field intensities due to the remaining 5 masses will be acting along their directions. So this comes as E2, and here it is E3, and this one is E4, and this comes as E5, and finally this is E6. You can see from this point to each and every mass the distance is same. Let it be taken the distance is how much? X. Which means the distance from the point P to each and every mass is constant. We are taking it as X. We can express X in terms of the side length A also. Later we can see that. So the field intensity are acting in different directions, 6 different directions, but their values are same, their magnitudes are same. How much it is? You can write the magnitude of E1, which is equal to magnitude of E2, and so on, which is equal to magnitude of E6. All they are equal in magnitude, but they are acting in different directions. So how much is the angle between any two successive vectors? You can see, and this angle comes how much? Yes, this is the side length A. This length also comes as A. This is also A. It forms an equilateral triangle. How many you will get? 1, 2, 3, 4, 5, 6. 6 equilateral triangles are being existed in the regular hexagon. And this angle comes as how much? 60 degree. And to find the resultant of the two vectors with an angle, we can easily do by using the parallelogram law of vectors. No need that. How? Because if you look at this E1 vector, which is exactly opposite to E4 vector, there you can see E1 is exactly opposite to E4. And similarly, E2 is exactly opposite to E5. And E3 is exactly opposite to E6. As they are equal, and finally E1 is being cancelled with E4. These two will be cancelled out. And here E6 is being cancelled with E3, and similarly E2 is being cancelled with E5. All they are cancelled out, and finally you will get the resultant gravitational field intensity at the center of the regular hexagon is how much? The resultant value at the point P is equal to how much? 0. Even if you can take a triangle with 3 equal masses which are placed at the vertices, The resultant field intensity at the centroid, you can take the centroid. It is the point of intersection of the medians. And here is the point. The same thing. From this point to each and every mass, the distance is same. Let it be taken x, x, x. The side length you can take it as a. And here the x comes as a by root 3. By using geometry, we can find the x in terms of a, how much you will get? A by root 3. But it is not necessary because this mass will attract this point mass towards it in this direction. Let it be taken, this is A1. Similarly, this mass is attracting this point mass, unit mass along this direction. Let it be taken it as E2. And the same mass is being attracting this unit mass along this direction. And this is taken as E3. You can see 3 vectors which are acting at the same point. All they are equal in magnitude. Again, the same thing. E is equal to magnitude of E1 is equal to magnitude of E2 is equal to magnitude of E3. Because the masses are equal and the distance from point to the mass is constant, you will get their magnitudes are equal. And if 3 vectors are acting at a point, if they are equal in magnitude and they are making how much angle? 120 degree with each other. According to triangle of vectors, or we can say Lami's theorem, by the vector knowledge, we can say the resultant gravitational field intensity at the centroid is how much? 0. ER is equal to 0 at the centroid. So when we see the question with regular shaped structures like the triangle or regular hexagon or regular pentagon, if all the masses are being given constant, same, if it is asked the resultant gravitational field intensity at the centroid, there always the field intensity is how much? 0. So let us take this point as a granted, and no need to do any calculation part. By looking, we can take the resultant intensity is how much? 0. Suppose here, if I am taking a regular hexagon of a different masses, for example, so in this way I am taking the regular hexagon, and here the mass m, here also m. Here I am taking 2m mass, and here is m, m, and n. There you can see everything same as the previous figure. The only one difference is that at one particular point the mass is being changed. The mass m is changed into 2m. Now I am asking, what is the field intensity at the center of the regular hexagon? Is it is again comes as 0? No. Because and the field intensity along this direction, so you can see these 2 vectors are being cancelled out because same mass, same distance. And here also the masses are equal and the separation is same, and these vectors are also being cancelled out. But along this direction, how much the field intensity is acting in this direction? In the opposite direction, we are getting double the intensity. Why? Because here the mass is m, here 2m. The mass is increased 2 times. So the field intensity also increases how many times? 2 times. Because the separation distance from this point to the mass is constant for both the masses. How much the distance? X distance. Here also x distance. Now, taking the difference of these two, you will get the field intensity at this point. Or else, we can split this m into 2 parts, m plus n. You can imagine 2m as m plus n. For example, if you take m, this m and this m has been balanced out. They cancelled out. And the left part is one more mass has been existed at this point. And with one mass, I can take in this way. This is only the one mass which is left after cancelling all the field intensities at this point. And here is the point P. And the distance you can take it as x. And directly you will get the field intensity at this point due to the mass, the left mass, after cancelling out all the things. How much the result? E is equal to gm divided by x square. and x we can express in terms of the side length a. If it is given the side length is a, how we can calculate this distance? This also comes as a only, because here it forms an equilateral triangle. There you can see how many such triangles will be formed inside the regular hexagon? 6. So x also comes as a. Finally, you will get gm divided by a square. So there you can see, if all the masses are being equal, which is placed at 6 positions, the resulting gravitational field intensity at the center is how much? 0. But whenever, if we are changing any one mass there, instead of taking m, it is taken as 2m. So just you need to take 2m as m plus m. So one mass, due to one mass out of 2m, if you take one mass, the field intensity due to this part is being cancelled with the field intensity with this one, and the left part is one more mass is there. Imagine only one mass is there and the distance is x at this point p, and there you will get the resultant field intensity about only this mass. So how much? Gm by x square, which is equal to gm by a square. So in this way we can find the field intensity at the given point due to the distribution of masses. Sometimes you will get the null point, which means the resultant field intensity at the point becomes 0 by cancelling all the individual fields due to all the masses at that point.